So we're now going to begin our discussion of determinants. I think most of the students in this course have seen determinants previously, at least to some extent. So some of this is going to be review for practically everyone in the class. And yet I think practically everyone in the class, in fact, probably everyone in the class is going to learn at least something about determinants in this discussion that we're going to have. This will be a long discussion. It takes a while to go through all the various properties of determinants that are included in this course. So this is just the tip of the iceberg. So we'll start off with a definition, something called the IJ minor of a square matrix A. By the way, determinants only apply to square matrices, just specifically square matrices. Okay, so the IJ minor of a matrix is the smaller matrix, we'll call MIJ, that's obtained by crossing out the ith row and the jth column of the original matrix. So let's see an example. Here is a matrix A, and we're going to write down here the 2, 3 minor. So, well, 2 and 3, 2. It says we're going to cross out the second row of the original matrix A. And this, let's see here. Yeah. This 3, that being J, says we're going to cross out the third column of this original matrix. And now let's look at what remains from the original matrix. The only numbers that remain are these 4. Those 4 numbers are the 2, 3 minor of A. Okay, all right, so that's, again, the short version, just crossing out the indicated row and the indicated column from the original matrix. Hard to see how this would be relevant to anything, but it turns out that this is, again, connected closely to determinant. Determinant has amazing properties. Hard to see it coming. All right, so here's our definition of determinant. The determinant is defined recursively. So what that means is we're going to start off by giving an explicit definition for the easiest case of small 1-by-1 matrices, and then the subsequent definition for larger matrices will depend on our definition of smaller matrices. So let's go into the details. Given a 1-by-1 matrix, well, of course, if a matrix is 1-by-1, it only has one entry, and the determinant is that value. All right, very innocent definition. For a larger matrix, the determinant is defined by this formula. It's a big formula, certainly. So this is recursive. In particular, notice that this n-by-n determinant is defined in terms of determinants of n-1 by n-1 matrices. And I know these are n-1 by n-1 because they are minors. Right, and we saw from up here that minors are n-1 by n-1. Okay. All right. So let's see some examples of how this formula plays out. And there's a lot of notation there to wade through. Here's our first example. First thing I want to point out is there's a summation here. And this summation in particular is with the index j. Now, so j is the variable that's going to be changing as we go through this expression. So j will take on values starting at 1 and ending at n. All right. Now, in this formula, where is j? Well, it's the column number in this factor. This factor gets saying, well, I want to look at particular elements of my original matrix. So we're going to be changing columns. The column number that we'll be looking at will be ranging from 1 to n. Likewise, the column number that we'll be scratching out. Notice we're computing a minor here. We compute minors by scratching out corresponding row, corresponding column. Here we're scratching out the jth column. Okay. You'll notice as well that the entry here and the minor that we're looking at have the same indices. Okay, so we'll be looking at an element of the matrix and its corresponding minor. Right, we'll also be keeping track of J as part of this exponent. All right, now I will notice, furthermore though, that these elements that we're looking at, and furthermore the corresponding minors that we're looking at, always in the first row. Right, this is not an I, that's a 1. Always in the first row, per the definition that we're going to be using here. We'll talk later about different versions of this. Okay, all right, so let's crank one out. Let's consider this 2 by 2 matrix, and let's use this formula to write down the determinant. Let's see how this formula applies in this case. So, always in the top row, first row, I equals 1. Because of that. Okay. So we'll start off, though, in that first row. We'll start off with J equals 1, and that would say that we're in the first column, and so we're looking at this entry, which is just A. That, when J is equal to 1, that is what that factor is. And that's that. Okay. When J is equal to 2, this J here, when that's equal to 2, and keep in mind J goes from 1 to N, in this case N is 2. When J is equal to 2, of course we're always in the first row, J equals 2 means we're looking at that entry. And that's that term there. Now that factor in that second term. Okay. Right, we have a bunch of minus signs to keep track of. Negative 1 to the I plus J. When J is 1, you have that. When J is 2, you have that. Notice that in this case, this is altogether plus, and this is altogether minus. And then finally, let's look at the factors that are the minors, and particularly the determinants of the minors. Okay. Well, for this first term, notice that the entry that we're looking at the corresponding minor. So we're going to be crossing out the row and the column for that entry that we're already looking at. And the remaining, in this case, is just D. Right. And likewise, well, I should have left this here. Likewise, whoops, excuse me. The corresponding entry when you're looking in the when J equals 2, you're there. Cross out the row and the column, and what's left is C, which is that right there. So a bunch of different factors. Notice that in each case we have an element of the matrix, a certain number of minus signs, and a determinant of a corresponding minor. And you write down these terms that look like this. Right? You have one term for that entry, you have another term for that entry, and you go across that top row. Okay. Now I would encourage everyone to memorize this little formula. This is really useful, surprisingly often. Simple formula for a 2x2 determinant. A lot of students like to remember this by saying, well, you sort of multiply on the diagonals to get that term, and then you subtract the product on the off diagonal right there. So it's a nice little sort of memory tool. But note in particular, this is the special case, the 2x2 special case of this more general formula. Okay. All right, here's a 3x3 example. Now, going across the top row, notice we have the corresponding entries. Notice we have a certain number of minus ones. Right? When J equals 1, it's 1 plus 1. When J equals 2, it's 1 plus 2. When j equals 3, it's 1 plus 3. Okay. And then the corresponding minor determinants. Now let's look at these minor determinants one at a time. For the first entry, cross out the row and column, and we have that as the corresponding minor. Okay. For the second entry, cross out the row and the column, and we have these four numbers here as our corresponding minor. And in the last position, cross out the row and column, and we have that. So a bunch of details to compute. Now you can see the recursive nature of the formula here. We've used our definition on the previous page to write this 3 by 3 determinant, and it has come out as a formula involving 2 by 2 determinants. And we computed 2 by 2 determinants on the previous page to be this. We computed that from our knowledge of 1 by 1 determinants, which was given. Okay, so that's sort of the recursive nature. And so you've got to compute these 2 by 2 determinants from the formula on the previous page. There's a significant amount of arithmetic left, and the result is, as it happens in this case, the determinant 0. This is, by the way, side note, not a coincidence. And you'll notice I picked a deliberately boring matrix here, 1, 2, 3, 4, 5, 6, 7, 8, 9. The fact that that is boring is part of the reason why we got 0 here. And we'll see the details of how that works out, why, in some sense, that works very soon. All right. Here now is a theorem, and I emphasize this is not a definition, this is a theorem. In fact, this is a pretty significant and hard theorem to prove, at least in the context of Math216. This is an alternative formula for the determinant. That is an alternative to that. Now, at a glance, they look the same. Entry of the matrix, certain number of negative ones, determinant of a minor. Isn't that exactly the same as this? Entry of a matrix, certain number of negative ones, and determinant of a minor. Here's the difference. Here you will notice that the row number is not necessarily 1. Right? It's the same process where we're looking at a certain element of the matrix, a certain number of -1s, and determinant of the corresponding minor. That's the same, yes, but this is not in necessarily the first row. This could be any row. Okay. Also very surprising, this seemingly very, very similar looking formula. But this is very different. Here, this is a subtlety, you gotta devil's in the details. Notice that here it's not j that we're summing over. Here it's I. So here the row number is changing. And it's the column number that's fixed. J here is fixed and can be any value. Color code J. The column number that we're looking at could be fixed. So instead of, we think of this as going sort of across a row, this you can think of as going down a column. So this procedure of computing terms that look like this and adding up, not only do you not have to use the first row, you could use any row or any column. Remarkable that this works out. Now before we do an example, I want to talk about the negative ones. These negative 1 to the I plus j that you see in both of these formulas. And I just want to note that that negative 1 to the I plus j creates this checkerboard pattern, interestingly. So look at some cases. So in the first row, first column, of course, then we get negative 1 to the 1 plus 1, which is positive. Right? So we get a plus there. If you move over by one column, then you're going to have negative 1 to the 1 plus 2. That's going to be negative. Right? And then if you move over again, well, that'll be positive. You just keep track of the how many minuses do you have, and every time you move by one in either a row or a column, you get an extra minus sign, and therefore the sign changes, and thus you get this checkerboard pattern of pluses and minuses. So let's keep that in mind as we compute. So now I'm going to do the same computation, the determinant of this matrix. We're just going to do it with different rows and columns. So instead of going along the top row like I did before, let's go along the second row. And let's just see what happens. Well, here are the entries, 4, 5, and 6. Now let's think about our checkerboard pattern. Our checkerboard pattern of pluses and minuses. Plus, minus. It's not going to look very good there, is it? Here, I'll do it like this. Plus, minus, plus, minus, plus, minus, plus, minus, plus. And going across the second row, you can see we have minus, plus, minus. Okay. All right. And then the minors, well, you can do these one at a time, but looking at this number 4, we were at that position. Keep in mind we're in the second row. Cross out the row number and the column number, and you're left with these numbers here, etc. for the other terms. Okay. And you can do the arithmetic, and this will in fact give you the same value as the computation we did on the previous page. Likewise here, same calculation, it's just that now we're going down the third column. Down the third column, you get plus, minus, plus from the checkerboard pattern. The entries are 3, 6, 9. And the minors, well, again, you have to do these one at a time. But so, for example, for this 3 entry, cross out the row and column, and you're left with that. Okay. All right. Okay, so that's how you compute the determinant with cofactors. With the recursive definition, minors and etc. I do want to introduce a new definition, cofactors. I got ahead of myself. It's just a name, it's a label that we put on part of the formula that we use to compute determinants. This ij cofactor is the product of the minus signs and the minor determinant. So it's in our formulas here, it's that. That's the ij cofactor. Likewise that. Same exact expression. So calling this a cofactor and giving it a name, right, referring to it now as Cij, those formulas now turn into these formulas. Now, nothing's happened. We didn't change the formulas any. I just have an abbreviation now that this is an abbreviation for what had been the separately written minus signs and minor determinants. Who cares? Why would I do this? Are we really trying to save that much ink? Turns out there's a really good reason to do this. There's something wonderfully special about this formula, and likewise this formula, and we will see that in a later recording. Okay. All right. So I do want to prove one result. There's a surprising fact about determinants that we are now prepared to prove. Very surprisingly, when you take the transpose of a matrix, the determinant does not change. Pretty unexpected. Let's remind ourselves, our formula for determinant involves picking a row or a column, picking a row or a column, going across the row or the column, let's say a row here, and looking at the particular entries, and there's this whole -1 business and this corresponding minor determinant. Well, if you transpose a matrix, all the numbers move to different places. It's really not clear that you're going to get the same thing. On the other hand, going across a row of the transpose, you can kind of see, well, yeah, but that's the same as going across a column of the original matrix. So that part actually looks like it might be compatible. If indeed you can go across any row or column, you can see how transposing doesn't really, that's not that scary. The checkerboard pattern. This checkerboard pattern, when you transpose, minus goes to minus, plus goes to plus. Right? So that seems to fit pretty nicely. At a glance, it looks like it's surprising, but it's not the most surprising thing in the world. So I want to write down the proof of this. It's really just a matter of writing down details. We're going to do this proof by induction. The idea of an inductive proof is that we're going to start by proving the base case for a 1-by-1 matrix. Well, it's clearly true for a 1-by-1 matrix because the transpose of a 1-by-1 matrix is that matrix. So, of course, the determinant of this is equal to the determinant of that because, well, they're the same matrix. Okay. All right. So now let's suppose, as one does with induction, that we know that our result is true up to n-1 by n-1 matrices. And all we know is that it's true up to n-1 by n-1. And from that, we want to prove that the result is true for n by n matrices. Okay. So what we're going to do is directly compute the determinant of the transpose from our formula and just directly show that it's equal to the original determinant. And it's just a matter of being careful with the details. Now, the very first thing I write down here is just the definition. This is straight out of the definition for the determinant of a matrix. We're doing a expansion across the kth row here. You notice the kth row number there and there. The column number, L, ranging from 1 to n, right? Within the kth row. So this is our process of going across the kth row. Here we have the KL entry of our matrix. Here we have our minus signs. And now this notation here is intended to represent the corresponding minor. Now, I can't just call this M, right? M is a notation that we've used in the past to represent the minor, or one of the minors of the matrix A. Very importantly, this is not a minor of the matrix A. This is a minor of the matrix A transpose. So I can't just say M, and that's why I'm calling this M prime. Right, the prime is just an indication that this is a different minor. This is a minor of that transposed matrix. Okay, so in fact, all we have here is just the definition of this determinant. Okay. Well, not hard to see. That's equal to that. The KL entry of the transpose is the LK entry of the original matrix. That's a definition of a transpose. -1 to the K plus L is, of course, -1 to the L plus K, because K plus L is L plus K. So I haven't really done anything in either of those first two factors. Now, this is the tricky part. This matrix is the same as that matrix. We got to think through the details here. Keep in mind what we've got. We started with some matrix A, right? And let's look one side at a time. Let's start by looking at this. This says I want to transpose it and look at A transpose, and then cross out the kth row and the lth column of the transpose. So we're going to cross out the kth row and the lth column. Okay. All right. Now, what is this matrix? This matrix, we're still going to cross out a row and a column. There's still going to be a transpose. The important difference here is that here we are crossing out the row and column first, and then subsequently transposing. So here we're crossing out the lth row of the original matrix A, and then we're crossing out the kth column. All right. So, and then subsequently we're taking this and then transposing it. Okay. So, do we get the same thing? Well, I'd just like to point out that, in fact, we've done exactly the same thing, just sort of from a different point of view. So, what do I mean by that? Well, when we crossed out this kth row of the transpose, where did that kth row of the transpose come from? Well, it was the kth column of the original matrix. So in both of these, here and here, we're crossing out the exact same numbers. It's just that it's the kth column up here, it's the kth row there. Okay. Similarly, crossing out the lth row of the lth column of the transpose, crossing out that lth row, that lth column of the transpose. Well, the lth column of the transpose is exactly the lth row of the original matrix. So in both cases, we're crossing out exactly the same numbers and then transposing. And whether you cross out those numbers before you transpose or after, you're still throwing away the exact same numbers. So even though these look different, the important observation to make here is that these two matrices are identical, and therefore, of course, their determinants are the same. Okay, so that's the big step in this proof. With that observed, looking at this factor, the determinant of this minor, well, this is an n minus 1 by n minus 1 matrix. We already know that transpose preserves determinant. So this transpose didn't do anything. So again, keep in mind we're assuming that the result is true for n minus 1 by n minus 1 matrices. So we know that's equal to that. And now you look at this formula here, and it is exactly the determinant of the original matrix A. This is a kth column cofactor expansion for the determinant of A. And so just take this formula and look and confirm that this is, per a couple of pages ago, exactly that formula. Okay, so this proves our result that transpose does not affect determinants.